substitution
Okay.
with the quadratic formula.
Okay.
I think is what he called it. I don't know. Okay.
Well, it's just using the quadratic formula to solve a quadratic.
Yeah. Alright, one second. I have to find it in my book. These numbers.
Now, the best way to practice these is just to come up with some quadratics and try to solve them.
Alright. I have problems in the book.
Okay.
If I can find them ever. Okay, no, that's not what we did today. Oh god. Alright. I can't find the problems in the book. I know I have them somewhere, but maybe it's these quadratic functions. The ones where you put the like substitute a variable for, I don't know how to explain it. You have a quadratic, like you have
How do you solve that?
the quadratic functions, I think.
How do you solve this quadratic?
Are
Are there any factors of 10 that subtract to the number 1?
No.
Okay, which means you cannot solve it the typical way by factoring it. So the solution is x equals what? It's the quadratic formula?
1.
Minus,
Right.
well, let's write the general formula. It's always a good idea to put that up there first.
Plus or minus the square root of b squared minus 4ac all over 2a.
And I think it's also a good idea to spell out what A, B, and C are. If you have any confusion about it at all. What's A?
1,
What's B?
-1,
And what's C?
-10.
That's all there is to using the quadratic formula every single time. In other words, it's the easiest thing in the world to do. Simplifying is not so easy. So let's go ahead and plug this in. What's negative B?
1, because it's negative.
B squared. Fill in the rest for me.
So 1 and then -4 times -10, so plus 40?
Well, first of all, 4 times 1
Isn't 4?
times -10. So yes, 4 plus 40 all over 2. And then this equals 1 plus or minus what?
Yeah, over 2.
What's the result of inside the radical?
1 plus 40. 41, but
Okay.
yeah.
Now, does 41 simplify? Is that a prime number? Yeah, that is prime. I can't even think of any factors of 41. So, what is our answer for x in this problem? You usually get 2 answers for a quadratic. What are they?
This one would be 1/2 plus 41 plus the square root of 41. And
Over
then
2.
1/2 over 2.
Over 2.
And then the other one would be 1/2 minus the square root of 41 over 2.
Right. And I like separating it into 2 pieces like that. Even though it's not required, you could actually give that as an answer. But when you have complex solutions, in other words, when this discriminant is negative, you're going to have I. And in I, when you have complex numbers, you always want to give them in the form A plus BI, where that's the real part, that's the imaginary part. Well, this is not a complex number, but we're still giving the rational part and the irrational part. We separate them. Okay?
Alright, I'm sure I have problems with this.
Go ahead and take a second to look, because I want to do the problems you're covering.
Yeah, okay, so we did a new thing today, and I think I got it. Oh, well, see, here's the section, but they don't have the...
What's the new
I found
thing?
the problems.
What's the new thing? Okay, go ahead.
Okay, it was on, like, okay, yeah. So, see, the problems in the book didn't really match me. Yes, they do. I found one. So, it says, x squared plus 3 in parentheses squared minus 6 parentheses x squared plus 3 is equal to 7. And then you substitute in like a variable for the x squared plus 3 and then solve it that way.
Okay. In other words, they're saying this is a quadratic in disguise.
Yeah.
Right? That's what I call them. In other words, let's use u to represent x squared plus 3. Then what we have is u squared minus 6u minus 7 equals 0, which is a very easy quadratic to solve. How's this factor?
Oh, duh. 7 and negative 1. Negative 7 and positive 1. Right?
Uh-huh. Which means the solution now is, go back and resubstitute. So we have x squared plus 3 minus 7, so that's x squared minus 4, times x squared plus 3 plus 1, which is x squared plus 4. And now what can we do?
You just make it...
This can be factored further.
Wait. You pull out... Could you pull out an x and a 4?
Well, what is this called? Difference
of squares?
Always learn to recognize difference of squares.
Yeah.
In other words, when you look at binomial terms like this, first thought in your head should be, is this the difference of squares? Because it usually is. So how can I factor that?
X minus 2 and then x plus 2.
Uh-huh. And then what about x squared plus 4?
I don't think so.
No, it doesn't. The sum of squares does not factor further. The sum of any even exponents don't factor. The cubed, odd numbers, does, oddly enough. If I had a cubed plus b cubed, that does factor, but not the sum of squares. That's an irreducible quadratic. All right, so now let's solve this. What's the next step in coming up with an answer for x?
Substituting your answers in?
No. It's the fundamental theorem of algebra, say.
X is equal to stuff? I don't...
If you multiply things together and they equal 0, then one of them has to be 0.
Okay.
So the way we solve this is we let each one of these three things equal 0 and solve for x. So I'm going to let x minus 2 equal 0. So what's x equal?
So 2.
Okay, that's one solution. Then I'm going to let x plus 2 equal 0. What's that x equal?
Negative 2.
And then I'm going to let x squared plus 4 equal 0, or x squared equal minus 4. And what do I do here?
You take the square roots.
Okay, so now what? X is equal to what?
2i.
Plus or
Plus or
minus 2i. Very important. And because notice if you forget that plus or minus, this thing only has 3 solutions. And yet it's a quartic. If I multiply everything together, I get x to the 4th. So it's a quartic polynomial, which means it needs 4 solutions. Cubics are going to have 3, quadratics are going to have 2, quartics have 4. So if you find yourself coming up with 3, you've left off one. And usually it's either the plus or minus. And also remember that complex solutions come in pairs. You cannot have a complex solution of 2i without having a minus 2i. Whenever you solve quadratics or any polynomials, and they give you, say they give you a 4th degree polynomial, and they tell you that 3 plus 2i is one solution. That's 1, 0. Well, that means that 3 minus 2i is another solution, for sure, 100%. So now you have 2 out of the 4. You can divide these into the quartic to reduce it to a cubic, and then divide that by that to reduce it to a quadratic. And you can always solve quadratics by using the quadratic formula.
Right.
Okay?
Okay. Okay. So x plus 3 in parentheses squared minus 5 parentheses x plus 3 plus 4 equals 0.
Okay, work me through it.
Okay, so I guess I'll use z maybe. So then,
Z?
yeah,
Okay.
then x plus 3 would be equal to z.
Okay.
And you substitute that in, so you get z squared minus 5z plus 4 equals 0.
Okay.
And then you can't put that into or you can't factor it.
You can factor it, but you can also, it's very important to realize that you can also use the quadratic formula, and it'll give you the same answer. In other words, the quadratic formula works for every quadratic. Factoring only works for quadratics that factor nicely, which
Okay, yeah.
this does.
I see how you can factor it now. Blonde moment. I'm not even blonde. So minus 4 and then z plus 1, or minus 1.
Uh-huh.
And so then you get your answers for z.
Well, we got 2 choices here. We can solve for z, and once we get a solve for z, we can go back and solve for x. But why don't we just put in this immediately before we go further? Back in for z. Is that what the teacher did, or did the teacher wait and solve for z and then give you the solution for x?
He showed us 2 ways to do it. The way he said that we can do it your way, where you just put it right back in there.
Mm-hmm.
But then the other way we did it was you would get 4 and 1 for this problem.
Okay, let's do it the other way. Z equals 1, z equals 4. So if z equals 1, what does x equal?
Then x equals negative 2.
And if z equal 4, what does x equal?
And then z equals, or x equals 1.
Okay, so there's the two solutions, and we solved for z the first time. Okay, notice that if we do it the other way, it'll give us the same two solutions. In other words, if I plug in x plus 3 minus 1 would be x plus 2. If I plug in x plus 3 minus 4, that's x minus 1. And then if I solve those, I get that and that. So it's the same way either way. Whichever way you feel more comfortable with. I would use one way and stick with it.
Alright. Just like pick your way.
Yeah. Now, some of these you can probably even use the quadratic formula on if you had to. That would be the hardest type. In other words, where you have to use substitution and it still doesn't factor, which means you have to use the quadratic. I don't know if he's going to give you any that hard or not.
I think, oh, some of these look pretty.
We can try them.
I found a nasty looking one. We could try
Let's
that
do
one.
it.
I don't think it's, well, I guess it is, because it's a square root. Okay. So, so you have 3 over n minus 7 over the square root of n minus 6 is equal to 0. Yeah.
Okay.
So,
Any ideas?
well, not really.
Well, we could actually do a couple of things here. What I would do is multiply every term by n.
Okay.
I can always multiply everything by n, both sides. Now what do we have?
You get 3 minus 7 over n. Would it be 7n over n, or just 7n?
Be 7 for the moment. We'll leave it like this.
Okay. Minus 6n is equal to still 0.
And what is n over square root of n equal to?
Well, that's n squared divided by, would it be equal to just n? N to the power of 1?
What's that equal to? Same base, different exponents. We're doing division. What do we do with the exponents? So this is equal to n to the 1/2, square root of n. Okay, so I'm going to write square root of n there. Now we have still a quadratic. You might not recognize it as a quadratic, but notice that this term is the square of this term. And there's your constant. So let me write it as, let me divide everything by minus 1 and write it in the proper order. So I have 6n plus 7n to the 1/2 minus 3 equals 0. Now it's getting to be more recognizable as a quadratic. So z is going to be what? I'm going to use my substitution technique.
This is where we get.
This is the tricky part.
Would it?
Z is always the middle term. n to the 1/2.
Okay.
Because after we convert it to a quadratic in z, we want z to be the middle term. We want z squared to be the front term. So if z equals n to the 1/2, how can I write 6n?
Okay. 6 squared?
Yeah, 6z squared.
Oh, sorry. Yeah.
Plus what?
Plus 7 and
7z. And that's the key. That's how we picked what to use for substitution, because when we were done substituting, we want this to be a normal looking quadratic, and a normal looking quadratic has z as the middle term, not z to the 1/2. And a normal looking quadratic has z squared as the first term. So notice in all those other problems, we used that as the thing that we were going to substitute for. Notice that that is the variable of the middle term.
All right.
Up here, that middle term was x squared plus 3. So that was our z. The whole point of the substitution is when you get done, you want z squared plus some number of z plus your constant. Because now we can probably factor this. I'll bet you this does factor. Just because I would be surprised if they made it that difficult. Help me factor this. Hopefully it won't factor, and then we'll use the quadratic, and I'll show you how to use that.
Okay. So you have to get it to...
First of all, we got to factor that first term. It's not z and z. What is it?
It could be 2 and 3.
I always start out with the two closest factors. It could be 6 and 1, and if none of these work, we'll have to try 6 and 1. But let's try 3 and 2 first. Luckily, there aren't very many factors for the constant, so I know it's 3 and 1. But it can be plus 3 minus 1. It could be minus 3 plus 1. Let's just try it until we find one that works. Does this work?
No.
Okay, let's try the 1 over there and the 3 over here. Does that work?
No, if the 3 was negative...
It works. It gives you the right number. It just doesn't give you the right sign, right?
Yeah, so 1 has to be...
Right. So all I have to do to fix that is to change the signs. So it's minus 1 plus 3. Notice that I could not use any of my descriptions to factor this. I could not say factors of 3 that subtract to 7. I couldn't say factors of 3 that add to 7. You can't do that if there's coefficients in front of the variable.
Okay.
Okay? You just kind of have to use trial and error. But they don't generally make it too tough for you. If you always try the factors that are closest together, then you just have to try 4 possibilities here. I had to try minus 1 plus 3, minus 3 plus 1, and then the opposite 2. Okay, so let's do it your way and solve for z, first of all.
All right. So they're all equal to 1. You have 3z. So you get z equals 1/3.
Okay.
And then you got z is equal to -3 over 2.
Okay. So now let's solve for n.
Alright, so, oh goodness Lord.
For this one here, n is what?
Okay, 1 second. Well, thinking.
So I'm going to substitute 1/3 for z
Yeah, but then
and solve for n. How do you solve that for n?
would you multiply them by, would you square them both?
Square them both, exactly. So that n is equal to 1/9. And the other n?
It would be, okay, -9/4?
Positive
Or
or
9 over
negative?
4? Positive.
Positive, because we have to square both sides. So that n is equal to 9/4. So we got 1/9 and 9/4. Let's go back in and see if that works into our original equation right here. So what did I say? 1/9 and 9/4. So let's try 1/9. So 3 divided by 1/9 is how much?
Would be 1/3. No.
3
No.
divided by 1/9. How do you divide by a fraction?
Do you have to multiply by?
You flip it and multiply. Don't forget to flip it. In other words, it can't possibly be right to multiply by the same thing that you're trying to divide by. Right? So only if you change this can you then change it into a multiplication problem. So dividing by 1/9 is the same as multiplying by 9/1. That's equal to 27. So that's 27. What's 7 over the square root of 1/9?
Okay.
Remember when you take the square roots of fractions, it's always a good thing to remember is that they're going to get bigger. They don't get smaller, they get bigger. You take the square roots of numbers bigger than 1 and they get smaller. But you take the square root of 1/4, it's 1/2. So what's the square root of 1/9?
1/3.
And what's 7 divided by 1/3?
Well, 21.
So that works. So this solution works. Now let's try the other solution. Wouldn't necessarily do this every time, but in this case it's worth doing. So 3 divided by 9/4, what's that equal to?
4/9, so you get 12/9.
Which is 4/3.
Yeah.
Minus 7 divided by the square root of 9/4, which is what? What's the square root of 9/4?
3/2. 3/2.
Uh-huh. And what is
then
7 divided by 3/2?
14/3.
Okay. What's 4/3 minus 14/3?
10/3.
Plus
Negative.
or minus?
Negative. Negative 10/3.
So negative 10/3 minus 6 does not equal 0. So this is not a solution.
Is that because we squared it at the beginning of the problem?
It does have to do with the fact that there's a radical in there. When you're solving a quadratic, if it's a standard polynomial, you rarely create extraneous solutions. But if it has absolute values in it, you frequently create extraneous solutions. Or if it has radicals in it, you create extraneous solutions. Or if it has logarithms in it, you create extraneous solutions. So those are the 3 things that I know of, and trig functions. where you're liable to have an extraneous solution. And what we had here was a radical sign. So it doesn't surprise me that we had an extraneous solution.
Okay.
Now, let me think about this for a second. Is it possible that that first solution, that first step I did, wasn't the correct one? Let me think about that for a moment. Because what if we immediately, there's no question we're going to have to let z equal n to the 1/2. Okay? So that would give us 3 over z squared minus 7 over z minus 6 equals 0. Now I would multiply every term by z squared. So I have 3 minus 7z minus 6z squared equals 0. Divide everything by -1. We have 6z squared plus 7z minus 3 equals 0, and that's what we originally solved. So it didn't matter. It's correct the way we did it. And we did come up with 2 solutions, one of which was extraneous. And minus 9/4, in case you're wondering.
Yeah.
You want to check that and see if that's possibly a solution?
Yeah. Okay.
I'll do it real quick here. Minus 9/4. So 3 divided by minus 9/4 is minus 4/3. Well, notice immediately that we're going to try to take the square root of a negative number. So minus 9/4 could not be the answer. No negative number could be. And we didn't really come up with a negative number anyway. In other words, because z equals n to the 1/2, by plugging in minus 3/2 for z and solving for n, we got a positive 9/4. So there was nothing bogus about this solution coming up with it. It just didn't work. It wasn't. In other words, the fundamental theorem of algebra doesn't say that if you multiply 2 things together that's equal to 0, that both of them have to be 0. It merely says one of them must be 0. And in this case, 1 was.
Okay. I get this, I think,
Okay.
maybe.
Okay. It's an interesting technique. I can't say that I've run across too many algebra students that have presented the substitution method to me like that. You use substitution a lot when you get to higher math. When you get to pre-calc and calculus, this substitution method is really important. Let me give you another potential one. E to the 2x minus e to the x minus 2 equals 0. That is a quadratic. Doesn't necessarily look like 1 because e is a number and x is the variable. But notice that if I let z equal, what would I let z equal?
E, the middle term, x.
E to the x. Now this first expression turns into, well, what's e to the 2x? That's z squared, right? E to the x times e to the x is e to the 2x. So this becomes z squared minus z minus 2 equals 0. This factors z minus 2 times z plus 1, and I get z equals -1 or 2. So when I plug -1 in for that, that's not possible. You can't take e to any exponent and get -1. So that's a bogus solution. But if I plug in 2 the other solution we came up with for z. Now I can solve that. Take the natural log of both sides, I get I get x equal natural log of 2. And that is the solution. Have you had logs yet?
Nope.
Not? Okay, so I'm way off base here. But my point is that quadratics come in all forms. They don't just come in x squared plus x plus a constant. They can be trig functions, they can be exponential functions like this. That's not an algebraic function, that's exponential. And they can be the ones you've been giving me, where they don't look like quadratics, but when you use substitution, they turn into quadratics.
Jesus. So many things.
Well,
okay.
it's actually a really good thing because it allows us to solve problems like that. In other words,
I think it's really cool.
This would be a terribly difficult problem to solve if I didn't know that that was a quadratic. It's the only way I know how to solve it, you know, other than plugging it into Wolfram Alpha and having them solve it. But, all right, what other scary looking ones do you have?
Okay. Let's see here. Oh, I've got some with negative exponents.
Okay, let's do that one.
That could be cool. So x to the power of -4 plus 5x to the power of -2, I guess, minus 36 equals 0. Could you say, like, to the negative square?
To the -2 is right.
Yeah, okay.
What's my z going to be?
It's going to be...
It's always this right there.
So x to the... Okay.
X to
Yeah,
the
okay.
-2. Okay? No matter what kind of a disguised quadratic it is, your substitution is always this term. Just like in the last problem, we substituted square n to the 1/2. Actually, I should have substituted n to the -1/2. That would have made the problem easier. Because if I rewrite the original problem, let's go back to that problem for a moment. Really, it was 3n to the -1 minus 7n to the -1/2 minus 6. So I really should have made my substitution n to the -1/2. It was okay the way I did it. I came up with the right solution. But if you're going to use a formula for how to use substitution, I like this formula. Just always choose this term, and that's what you want to make your variable, your substituted variable. Because notice that if we do that, we immediately turn it into a quadratic. I don't have to do anything else. What's my quadratic in z?
Okay. Yeah, I got this. So then you would have x squared.
Not x, z.
Z. Oh, sorry, z squared.
Okay.
Z squared plus 5z is 36.
And you see where we get z squared from. In other words, z squared, if we take what we substituted over here, z squared is that times itself, which is x to the -4th. So it was okay to substitute z squared for that x to the -4th. That's exactly what z squared is. Okay, now factor this. We need factors of 36 that do what to 5?
Add to 5.
No, subtract. Always, whatever this sign is in front of the constant, that's what they have to do. They either have to add or subtract depending on what that is. In this case, they need to subtract.
So 9 and -4?
9 and 4. So all we're looking for is two numbers, 9 and 4. Okay? We know the sign has to be opposite. We've gotten that far before we even looked at factors of 36. So now we've found our two factors that subtract to the number 5. The bigger factor goes with the sign in the middle. There's the 9, there's the 4. That's the process. You always want to go through to factor. 4 steps. Figure out what the signs do, figure out what factors subtract or add to this number, and then put the bigger of those factors with the sign of the middle term. So, sorry, I meant Z. So my solutions for Z are,
You would get 9 and, or -9 and 4.
okay. Now we go back to this step, plug in -9 for Z, solve for X.
Okay. So you would square root it?
Now, how do you solve this? Might be easier to solve it if you write it differently. How else can I write x to the -2?
X squared times I?
No.
No.
One thing to remember about exponents. Negative exponents have nothing to do with negative numbers. They are not negative numbers. X to the -2, that minus means reciprocal, and then we square it. In other words, that's equal to 1 over x squared. That's all. Notice that x to the -2 is a positive number if x is positive.
Okay, so
So I'm going to rewrite this as 1 over x squared. Now it should be a little easier to solve. How do you solve that?
you'd take the square root of everything, right? And you
Okay. Let's get the x out of the denominator.
So multiply by x squared?
Yeah. So now we have -9x squared equals 1. Now what?
And then you could square root both sides.
Let's get rid of this coefficient.
Okay.
How about we divide both sides by -9? In other words, whenever you're solving an equation, your goal is to isolate the variable. So you do it one step at a time. Okay? We're not quite isolated yet. We have a coefficient in front and we have it squared. Well, this squared doesn't operate on the -9, so I can certainly divide both sides by -9. So x squared equals -1/9. So what does x equal?
You can put the radicals over both the top and the bottom of the fraction and get x is equal to,
We're going to take the square root of both sides,
yes, square root of 1.
plus or minus the square root of both sides.
Yeah.
So what is the square root of -1/9?
Well, it simplifies, so you get 3i on the bottom.
Yeah, it's 1/3 I. In other words, the way you do that is square root of -1/9 equals the square root of -1, there's the I part, times the square root of +1/9, right?
Yeah.
This is 1/3, this is I. So that's where I get my 1/3 I. And then the plus or minus came from the fact that we had to take the square root of both sides. So here was our original equation, and we're saying one solution, it's a quartic, notice, even though it's minus 4, it's still a quartic. So one solution is plus 1/3 I. The other solution is minus 1/3 I. It's good because they always come in pairs. So there's two more solutions, and that's going to provide them. So now I go back and I substitute 4 for z and solve that. What solution does that give you?
Okay. Well, the first thing you do this time, because we learned last time, is to multiply by the x squared.
There's numbers of ways to do it. That's my favorite, just because I don't like dealing with variables in denominators.
Yeah.
They're scary. Why? Because you can't ever divide by 0. So you got to be leery if your variable's in the denominator. But in this case, I'm certainly allowed to multiply by 0, so I don't have any problem multiplying by x squared. So x squared is equal to?
To 1 over 4.
And x is equal to?
Plus or minus the square root of 1 over 2.
No, it's the square root of 1 over 4, which is equal to 1 over 2.
Okay, got this.
Okay, in other words, x is equal to the square root of 1/4. And the square root of 1/4 is 1/2. Remember, square roots of fractions get bigger.
Right.
So there's our 4 solutions, plus 1/2, minus 1/2. So that was a good problem. Not only did it have 4 solutions that were tough to get at, but 2 of them were imaginary. So that had it all, except you still haven't run into one yet that didn't factor nicely after the substitution. In other words, where you would have to use the quadratic formula. But that really wouldn't present any problems. You'd still do exactly the same thing. It would just be a little more complex looking. Well, we got about 10 minutes, so we got time for another one.
All right. Okay.
These are almost 10-minute problems. They're pretty long. And I wouldn't say that you have to go back and check all 4 solutions. That'd be a lot of work to have to go back and check all 4 of these solutions into this function. I'm quite confident that all of them would work, but
All right.
that's because there was no radical signs at all. In other words, this equation really was 1 over x to the 4th plus 5 over x squared minus 36. Notice there's no radical signs. So we would not expect to get extraneous solutions. There's no absolute value signs, no logs. So
I'm trying to pick a good one.
okay.
Okay. So x minus 3 square root of x, 3 times the square root of x, minus 4 is equal to 0.
Ah. Okay. Z equals what?
Okay, I got this time. So z is equal to 3 and...
Not the coefficient, just the variable.
Just the variable? So x squared?
Just that. I mean, I know on the other one I said it was e to the x, so sometimes it's the variable if it's in the exponent, but in this case, it's just this part here. Okay? So this one turns into a real easy problem. What is it?
Oh, it does, doesn't it?
Yeah.
Okay, so z squared minus 3z minus 4.
Okay. I know you can solve that. Let me give you a slightly tougher one.
Okay.
This is as tough as it's going to be.
Oh God. Okay.
Z equal to?
Okay. X and 1/3. X to the power of 1/3.
Now rewrite it in Z.
So Z squared.
Notice that when you Z squared is X to the 2/3. Right? X to the 1/3 times X to the 1/3 is X to the 2/3. So, in other words, Z squared, if I square both sides, I get X to the 2/3. So that's where we get Z squared from. Okay? Minus Z minus 4 equals 0. Now this one doesn't factor. We'll choose the quadratic on it.
Also, we're gonna be all sorts of fun. Okay.
What is Z equal to?
Is equal to 1 plus or minus the square root of 1 minus 16 over 2a. 2. Yeah.
So that's what Z is equal to. Now what is X equal to?
Well,
Let's start with this equation right here and fill in for Z.
so,
There's the first Z.
and then the second is the same thing with minus.
Right. So what's X equal to?
Well,
How do I get X all by itself on one side of the equation, isolated?
number 6. Would it be like 1 over x? No.
Cube both sides.
Duh. Okay.
Okay, in other words, I want to cube the right side and cube the left side. That makes the right side X. And this is, after all, just a number. There's no variable in there. So convert that to a number, cube it, whatever that is, that's the answer. And then let's look at the negative answer that we got. Now, is that going to present any problems?
Yeah, because
This is a negative number, right? Square root of 17 is greater than 4. So this whole thing is going to be a negative number.
oh dear God. Okay.
That doesn't matter. In other words, when I cube a negative number, I still get a negative number. I get X equal whatever that number was. It retains its negative sign when you cube it. If I were to square it, it would turn into a positive. But when I cube it, it doesn't. You cube,
Okay.
minus 2 cubed is minus 8.
Yeah, so you get 1 over 8. Okay.
Well, I don't know what this translates to. You need a calculator, turn it into a decimal, and then cube it. But those are the two answers. So we do get a positive answer, we get a negative answer, and with cube roots, you don't tend to get extraneous results. So I'm not really very worried about getting an extraneous result here. I believe both of these answers are going to be correct. The reason you get extraneous results when you have radicals that mean square roots is because when you square a negative number it turns positive. That ends up getting in the way of one of the solutions. But with cube roots it's not true. In other words, the cube root of minus 8 is minus 2. The cube root of 8 is plus 2. There's no ambiguity at all. It's always with odd exponents. It has a definite sign. There's no plus or minuses. Even exponents, there's always plus or minuses.
Okay. So like if you multiplied something to the power of 5, it would keep its...
Yes. Minus 2 to the power of 5 is minus 32. And conversely, the roots of negative numbers retain. If I took the fifth root of minus 32, that is not plus or minus 2, it is minus 2.
Okay.
All right. That's a pretty good session. Those are good problems. I like that. Using substitution on things that don't look like they're quadratics.
Yeah.
Because a lot of times that's the only way to solve them. You can't believe how hard it is to solve a simple something like this. A simple cubic. We have no cubic formula like we have a quadratic formula. This does not solve easy. This is probably a 20-minute problem to do manually. No kidding. Really is. And to the fourth power is even harder. To the fifth and sixth power, I mean, don't even think about it. It's a whole day problem. But so if you can take a cubic or a quartic and make it look like a quadratic, it really simplifies its solution. So it's a valuable thing to be able to do. It's just you can't do it very often. That's why I don't see it. It's a real special case where you can do it, where you have something that fits the quadratic formula by just substituting something for it. That's pretty rare.
Could you do it where, like, you pull something out, like you pull out x to the power of 4, so the original equation looks like z would be equal to x to the power of 4? So then you just have to do it like 3 or 4 times? Like you substitute 3 or 4 different times?
Yeah, in other words, if I had this, then I would let z equal x to the 4th, turning this into z squared minus z minus 2 equals 0, which factors nicely. Then it gives you solutions of z minus 2 times z plus 1. So my solutions are minus 1 and 2. And notice that does make it a little more difficult to solve. In other words, when I plug in minus 1 equals x to the 4th, now you're talking solutions.
Yeah.
There are 4 solutions to this problem right here. But the math, to give them all to you, is very high level. But there still are 4 solutions. Some of them might be the same. But anyway, let's not get into that part of that. But yeah, whenever the key to using substitution to turn a polynomial into a quadratic is that this is always half of that. Notice that when I had x to the 2/3 minus x to the 3rd, I knew that was a quadratic because 2/3 is twice 1/3. I could have used 4/3 and 2/3. Same thing. If it was 1/4 and 2/3, I can't do it. I can no longer solve this using substitution. Because I can't let z equal x to the 1/4, because then z squared is not equal to this thing. So using substitution is pretty unique. Sometimes you can use it. You should look for it, but it's not always going to work. All right. We're set for Sunday at 3? No.
Monday.
Oh, we changed it?
Yeah.
Okay. I will talk to you Monday. At what time?
Right.
What was it, 3?
I think it was 5:45.
Let me just pull it up here real quick. I can do it in a second. If I from my computer, I'm sure, that opens up all of these windows whenever I open up Google. Of course, GoToMeeting doesn't like me doing anything. 5:45. I'll see you then. Well, hold on. That's last week. Next week. You know, I don't have you on.
Did we not switch it?
No, we didn't switch it for next week. We switched it for last week. Did you want to make that a permanent switch?
Oh, yeah, I think so.
Ah, okay. So here, let me do this. Let's see. I think I can do this too, like this. So we're going to put it down here at 5:45, and I'm going to do that for all of them. Sure, of course. Have conflicts because I sent somebody else in there. All right, you're on at 5:45. I'll have to play with my software here to get it working right. But so Wednesdays and Mondays. Okay. Talk to you Monday.
All right, thank you.
Bye-bye.
Bye.